So today's lesson is on the periodic trends. So we just learned all about the organization of the periodic table and how elements within the same group or family have the same number of valence electrons. We're going to now learn how this information and how the electron configurations actually create some patterns of some special properties within the periodic table. So what we're needing for today is our notes page. I'm also going to be kind of drawing some things on our notes page with some colors. So if you would like to get out the same colors that I have orange, I have green, and I have blue. It is not required for you to do the colors. It is also not required for you to do the same colors I am doing. I just find it to be helpful. We'll also need our periodic table. You can totally use the periodic table that we colored from last lesson with our special groups, or you can get a blank, fresh periodic table. It's totally up to you, but I'm excited to talk about the periodic trends today. So the periodic trends. Ooh, here's a new term for us. It is periodicity. So periodicity is the predictable repetition of properties due to the electron configurations of elements within the same group. So we mentioned, and I love these Bohr model things here, you guys, this is a sampling of my periodic table of some of the elements. And we know that everybody who's in group 1, look, they have 1 valence electron on their outermost energy level. Obviously, as I go down with that group, I'm going to be increasing the size because of the energy levels being added, but they all have 1 valence electron. So that reactivity is expected to be somewhat similar. And as you move across a period or across a row, you're adding electrons every single time until you get to group 18, my noble gases, who have a full valence shell of 8. Except for helium, we remember the first energy level of full valence for that would be considered only 2 electrons because there is only an S sublevel or an S room on that first energy level. So our first out of the 4 periodic trends we're going to talk about today is atomic radius. So as you can see, the picture on this slide is a little sampling of a section of the periodic table showing kind of relative sizes of some of these atoms. So let's talk about why stuff gets real big down here and why stuff is real small up here. So let's define what atomic radius is. Check out this super sciencey definition. Atomic radius is 1/2 the distance between the nuclei of identical atoms that are bonded together. Meaning if I put atoms together and I say you are in a bond, the atomic radius is defined as 1/2 of the distance between the nucleus and the outside of the atom. Okay? So let's get honest here. Basically, we're talking about the size of an atom, of an element, okay? If we are measuring relative atomic radiuses, not actual numerical measurements, we're just kind of seeing how big or how small they are, right? So here's my trend for atomic radius, okay? Once again, I have little pictures here showing the relative sizes. My trend lines, meaning my arrows, when I will draw them for this lesson, will always show the arrowhead pointing in the direction where that trend increases. So I'm noticing here as I go down a group, it is increasing down a group, which just means my atomic radius is increasing. My atomic radius is getting bigger, and that's what we see here. Now, across a period, I have my arrow going this way. So remember, my arrow shows the direction of an increase in a trend. So if I'm looking across a period, it looks like my atomic radius increases going that way, or from right to left. You could also say if I'm going against the arrow or the other way, that would show the direction of a trend decreasing. So the big thing here is that where my arrows are pointing to shows the increasing in that trend. That was a long tangent, but I thought we had established this right now before we start talking about a lot of the trends. Okay. So my trend of atomic radius, as we just mentioned, is everything gets big down here at the bottom left of my periodic table. So there is increasing down a group, and we could say there's decreasing in size across a period. And the result of that is the opposite corner from my trend lines pointing to is this is where we're going to have the smallest elements on my periodic table. So this is great. We're like, great, we know where things are big and where things are small. Done. Move on to the next trend. No. The biggest part about our periodic trend lesson is knowing the why these trends happen, which I'm really excited to talk about. All right, let's talk about why atomic radius increases going down a group. Why? Well, as I go down a group, atoms get larger because the atom will occupy more energy levels. We talked about this last lesson. We know if I drop down a group, you guys, I'm adding a new energy level that's going to create a different valence, right? Well, as a result of adding more energy levels, those outer electrons are going to be pushed away from the nucleus due to something that's called electron shielding from the inner electrons. Okay, let's kind of unpack that a little bit more because that's kind of a wackadoo concept. Shielding. Okay, so let's pretend here's a little section of a Bohr model of an atom. Here's my nucleus. Do not worry about Z. That's just a typical term for like protons, our atomic number. I've got my valence electrons here, my outer electrons here on this outer shell. But there is another energy level in between that valence shell and the nucleus. Now, we know that electrons are negative and they are going to want to repel. So what actually ends up happening is that this repulsion in between the energy levels helps push outer energy levels farther and farther away. That's called electron shielding. The fact that these electrons in between my nucleus and my outer electrons are there, they are going to shield the outer electrons from that nuclear pull in some way. Basically, what we're looking at here is that as I add energy levels, though, the size of that atom increases, which is why we see that trend going down a group. Okay, now let's talk about across a period. So across a period, your atoms get smaller as you go from left to right because of an increasing nuclear charge. When I talk about nuclear charge, I'm talking about the part of the nucleus that has a charge. It is not neutrons. It is the protons on the inside. They have a positive charge. Let's talk about why this is important. Well, to pull in my energy levels with electrons, that positive charge is going to be attracting those negative electrons. So as I add a new proton, as I move across the periodic table, we know I'm increasing my atomic number, right? So if I'm increasing my atomic number, that is literally me showing a new proton being popped into that nucleus. And as I'm adding new protons into that nucleus, that nuclear charge is getting stronger. And its ability to pull those electrons in closer is much, much greater. You're like, but we're also adding electrons when we move across a period. Yes, but we are not adding electrons in other further away energy levels. We're adding electrons still within that same energy level across the period, so that nuclear charge is just showing its effect on that consistency of the same energy level. So the way that we would say this is that atomic radius decreases as I'm going from right to left across, or left to right across a period. So I can see here visually that, oh my gosh, I'm tracking this and it is so getting smaller. But as I mentioned at the beginning of this lesson, my arrows always show the direction that the trend is increasing, to where I would see my big atoms over here to the left side of my period and my small atoms over there to the right. Okay, let's kind of unpack this a little bit more. So here I want to kind of zoom in on lithium and beryllium. So lithium, he's got 1 valence electron, and beryllium, he's got 2. Lithium is atomic number 3. Beryllium is atomic number 4. Now let's see what that actually does. So here I've got my lithium atom, right? And here I've got my beryllium atom. I've just realized that these Bohr models are terrible. We would know that this should have 2 energy levels with 2 of the electrons spinning around on the inside here on the first, and just that 1 on the outside, that second energy level. Same thing for beryllium. We should see 2 electrons on the first energy level and the other 2 on the second energy level. No matter, this is doing a great job of showing us the relative sizes. So here we know lithium, he's got 3 protons. Beryllium's got 4 protons. So beryllium has a greater nuclear charge. So his pull on those electrons are going to be stronger, and therefore he will be smaller in a smaller atomic radius. Okay, what I thought we would do is I thought we could bounce on down here. And you guys have a picture, a little picture of a periodic table here. And I thought maybe with one of our colors, we could kind of summarize these trends. Okay, I'm going to use orange. I know on the PowerPoint slides there was yellow, but I feel like yellow is just probably not going to show up very good for us. But on my little mini periodic table right here, I thought we could write the trend lines for atomic radius, right? We know it increases going down a group and it decreases going from left to right across a period, which means the big atoms are to the left side of the period, So down here is where my big atoms are. Everything is trending towards being big in that bottom left corner, which means up here I've got my small stuff going on. Okay? We are also, this shows my trend down a group. It is literally showing my energy levels. I love this visual right here. So you know what, you guys, we are actually going to add a trend line to this picture too. We're going to draw a line down and we're going to say, oh yes, we know that that line down means up here we are small. And as we go down, we get big. Yeah? And now here's our visual of what's happening as I go across a period. I am getting smaller. It is decreasing across a period. So I would like to show my arrow in the direction that is increasing, right? In this section where the top of my arrowhead or the arrowhead is pointing to is where my atom is big. And then I can see the decrease over here to a small atom. Yes. Okay. So now let's see. I kind of want to maybe play some games. So here's a game that we are going to play. I'm going to have my little cute trend line periodic table right here in the frame so we can remind ourselves as we're going through these questions, like, okay, that's where things are going to get big. We know that it increases down a period, or the atoms get bigger as I go down a period, and they get smaller as I go left to right. So this first question is, which has the larger atomic radius? Carbon or oxygen? Well, we know stuff gets smaller as I go from left to right because of that increasing nuclear charge. Oxygen's got more protons than carbon, so he's going to squeeze his electrons in tighter. He will be smaller. So the answer to this question on which is larger is going to be carbon. So like I said, atomic radius decreases from left to right in a period because the greater number of protons in the nucleus will exert a greater attraction on the electrons, which pulls them in closer. So your atom gets smaller. Oh boy, this is super fun. Okay, it's like a game. I'm so excited about this. Okay, next one. Ooh, I'm comparing two things in a group. So my mind is already kind of thinking this way, maybe using this visual here to help me answer this question. So we are looking at lithium and potassium. They're saying which has the smaller atomic size, lithium or potassium? Well, we know as we go down a group, things get bigger because I'm adding energy levels as I drop down, right? So the smaller atom is going to be the one with the fewer energy levels, which is going to be lithium. So atomic radius increases down a group because atoms have more energy levels, which are located further away from the nucleus. You could say the opposite of that, as atomic radius decreases, meaning I get smaller if I go up a group because you are having fewer and fewer energy levels. That was very fun. All right, we're going to do some learning check questions, okay? If you want to have your actual periodic table up, because I'm not going to show you on my screen where the things are. So it says, is a barium atom larger or smaller than a strontium atom? Well, first of all, I got to find these elements on my periodic table and see if they are in the same group or in the same period or wherever. So I got, which one is that? Barium and strontium. Let's see. So barium is down here, right? And then strontium is right above him. So I'm comparing two elements in the same group. So already I'm visualizing. Same group, yes, energy levels get bigger as I go down. The question is asking, is barium larger or smaller than strontium? Well, barium is down that group a little bit further than strontium. So barium is going to be larger. Okay. Next question is if a halogen and an alkali metal are in the same period, which means same row, which one of those elements will have a larger atomic radius? So as a review, my alkali metals are group 1 over here on the very far left side. And then if I scooch it all on over, my halogens are over here in group 17, further almost to the end, right next to the noble gases. So if I were to pick one halogen and one alkali metal in the same period, and maybe using my small guy. So one guy over here and one guy over here in the same row, and they are asking which one will be larger. So I'm visualizing what happens to atomic radius as I go across a period, go across a row. Oh, they get smaller. So if they're saying which one is larger, the alkali metal or the halogen, we would definitely say the alkali metal, right? And then the last question is, compared to the atomic radius of a sodium atom, the atomic radius of a magnesium atom is smaller. Let's see if that makes sense. Let's find sodium and magnesium. So I'm finding sodium and magnesium. They're right next to each other. We are comparing them. They're in the same period. Okay? So they're telling us that sodium or magnesium is smaller. Yeah, that makes sense because as I move left to right, I am increasing that nuclear charge and it pulls it in tighter. So the smaller radius is primarily a result of the magnesium having a larger nuclear charge, right? More protons pulling those electrons in. Okay, let's see. Oh, let's talk about our next trend. So our next trend, I kind of like to think about it as a little subcategory trend of atomic radius. Ionic radius, we know what an ion is. An ion is an atom that has either lost electrons to become a cation in positive or has gained electrons in order to become an anion in negative. So ionic radius is just how big the ion version is of the element. Okay. So the overall trend, well, first of all, remember cations are positive. Another fun joke to kind of break up the monotony of the periodic trends. It says, atom number 1 says, I think I just lost an electron. Atom number 2 says, are you sure? Atom 1 says, yeah, I'm positive. Okay, so here's the overall trend of our ionic radius. The only reason why I kind of broke it up into 2 categories is because there is a slight difference between my metal ions and my non-metal ions. We actually talked last lesson that metals are the ones that become ions by losing electrons. And we mentioned last lesson that my non-metals over here, they become ions not by losing, but by gaining. Okay, so their processes of ionization, whether they gain or lose, are different. But if I look at them collectively on my periodic table, they all seem to have this same general trend, kind of like my atomic radius did. So I like to think of this ionic radius trend as being a subcategory of atomic radius because it's basically the same thing. Okay, but the root of this lesson here is we want to compare the original neutral atom size to the size of the ion, okay? So this first section says metal cations. We remember from last lesson that metals, they lose. So yes, that makes sense. They become cations. Metals lose electrons, so metal cations are smaller than the neutral atom. We kind of had a little bit of a preview of this last time I saw you guys. It says when an atom loses an electron, it loses it from its outer energy level. As a result, the remaining electrons are drawn closer to the nucleus. So cations have one fewer energy level, and therefore they take up less space. That kind of makes a lot of sense. If I'm comparing the sodium neutral atom to its ion, well, first of all, we know sodium, it makes sense for him to lose an electron and lose only one electron because he is in the alkali metals group 1 where they have one valence electron, which means they lose it. Lots of words right here. But yes, and in the process of that happening, you guys, this third energy level, poof, it's gone. I got no electrons occupying it. So the atom itself is going to be smaller. So what I'd like for us to do is, I think we have on our notes page, I would like for us to write some of these things that I've written here. So here is our metal cation. I want us to write Na. So that is the symbol for a neutral sodium atom. And we are going to write bigger. I want us to add those words to our picture. I mean, obviously you could see that looks bigger, but we may need some help down here when we talk about nonmetals. So that Na is bigger. Now this, the sodium ion, is Na plus, right? So Na plus. And he is going to be smaller. Very cute, very fun. I also now would like to take the opportunity, well, before I forget, is for us to draw our trend lines for our ionic radius. It is exactly the same, right? Where once again the arrow is showing the direction that the trend is increasing. So here's my big guys, my big ions, and here's my small guys, my small ions, right? And if you would like to, remember we showed in that first original picture that we got metals and non-metals, but that direction of the trend is totally the same. Okay, that's very cute, very fun. Okay, let's see what happens when I start talking about maybe well, first of all, we're not ready to talk about that. I like this visual. So this shows actually the first 3 alkali metals going down group 1. So these over here in the darker gold are my neutral versions. Each one of these is showing an ionization, which means I'm kicking off an electron. And I love this because you can see for each example, lithium, when he becomes an ion, oh, he got smaller. Sodium, when he becomes an ion, oh, he got smaller. Potassium, when he became an ion, oh, he got smaller. But overall, you guys, if I were to look at all of these ions, yeah, they're getting bigger as I go down a group. Okay, so the trend is the same. Very cute, very fun. Okay, now let's talk about nonmetal anions. So nonmetals, we know, gain electrons. So nonmetal anions are larger than the neutral atom. When an atom gains an electron, it adds it to its outer energy level, and as a result, the electrons are pushed farther away from the nucleus. Anions have more electrons in their outermost energy level and therefore take up more space. This one is not as quite easy to visualize because I'm not doing anything like adding more energy levels or taking away energy levels where you can see a drastic change in size. But what is actually happening is to keep in mind that electrons are all negatively charged to where when I pack a lot of them in the same space, they're going to do whatever it takes for them to repel each other. So here, my neutral chlorine atom, he originally had 7 valence electrons, which makes sense because chlorine is a halogen. He's got 7 valence electrons. Okay, also makes sense that he is going to gain an electron to complete his octet, which is why all of the halogens have a -1 charge. Now, in the process of doing this, I went from having only 7 valence electrons in the outermost energy level to now having 8. Ooh, that is more electrons to have to like get away from each other. So they're going to make that outer energy level spread out a little bit more. So looking on our picture on our notes handout, let's see if we can document that. So here's my anion formation. Once again, I can see the electron being added. And we are going to write here, this is my neutral atom, which is just chlorine, so Cl. And he is smaller, right? And over here, after gaining an electron, he becomes Cl-. And that Cl- ion is bigger. So kind of to recap here, my metals who lose, their ion is smaller than the original metal. My nonmetals who gain, their ion is bigger. So it's kind of like an opposite thing that you have to remember. But for me, I just try to kind of dumb it down in terms of like, hey, if I kick something off of my body, I'm gonna be smaller, right? And that's what that's what metals do here. Or if I add something to myself, I'm gonna be bigger. And that's kind of in simple terms what we're looking at here. Okay, and then I want us to see if we can look at some of the nonmetals forming their ions. Yes, so here are some halogens. I have fluorine, chlorine, and bromine. So these are my group 17 halogens. Yeah, that makes sense. They get bigger as I drop down that group because atomic radius trend increases because I'm adding energy levels. Well, same thing over here. It still gets bigger, okay, because there's still more energy levels. Comparing the original neutral atom to its ion that it makes, yes, these nonmetals get bigger when they form those anions because I am gaining an electron, which spreads those energy levels out further away from the nucleus. Cool. So here's another visual showing over here in green. We have a sampling of metals. Okay, the metal ion here is going to be the green versus the neutral metal is the gray in the background. So you can see to make the green, losing electrons, they get smaller. Now over here, for my nonmetals, the ion is this purple, okay? The neutral atom was this gray. So to become an ion, he goes from gray to purple. Yes, by gaining that electron, you get bigger, which is really cool and really exciting. Here we go, a learning check. I'm gonna bring out my periodic table so we can see it a little bit better. Let's see. It says, excuse me, is a sodium atom larger or smaller than a sodium ion? We may not need our periodic table for this, but sometimes I like to point at things. So sodium, he's here, he's alkali metal group 1. That makes sense that he has, as an ion, a +1 charge. What they're asking me is the neutral atom larger or smaller than the ion that it's going to make? Let's see. It's larger. The reason why that neutral atom is larger is because when he kicks off an electron to become an ion, he loses loses that valence shell and becomes smaller. So the neutral version of this sodium is going to be much larger than the than the ion. The next question says, in general, how does ionic radius vary from top to bottom within a group? So what happens as I go from top to bottom within a group? Does it increase or decrease, you guys? Let's see. It increases, exactly like atomic radius does. And then the last question says, which element will form an ion whose ionic radius is larger than its atomic radius? So they're asking me, which one of these things has an ion that's bigger than what it started off with? Well, to get bigger, that means I have to gain electrons, and gaining electrons, non-metals do that. So I'm looking at my list here. Potassium, he's a metal. Fluorine, he's a non-metal. I'm going to check the other ones just in case. Lithium, metal. Magnesium, metal. So the answer is fluorine, because fluorine is a non-metal who gains electrons, which means he will become larger when he is an ion. Good stuff. So now we're on the back. We're ready to talk about our third trend for categorizing ionic radius as a true trend. But this is called ionization energy. So we've got kind of a new term here. I got a picture here, and it literally is showing an electron flying off of the atom. And y'all, that is what ionization is. So let's unpack ionization energy. So ionization energy, by definition, is the amount of energy required to remove an electron from a neutral atom of an element. So basically, it's how hard is it to remove an electron? How much energy is required to rip an electron off of that valence shell of my atom? Okay, depending on where I am in the periodic table, you guys are probably guessing, some elements may want to very easily remove electrons, and some elements maybe really want to hold on to their electrons. And yeah, you would totally be correct with that. So let's kind of see what is happening there. So let's remind ourselves about the octet rule. Every now and then when we get into super sciencey terms like ionization energy, to not freak us out, I like to kind of explain it in a non-science language. So let's think about this. If an atom has one valence electron, like an alkali metal, it's going to be real easy to remove that one electron to get to that octet. The atom wants to do that anyway. That's why everybody in group 1 with one valence electron makes a +1 charge ion. But then over here in my noble gases, if an atom has a full octet, no, do not take an electron off of me. Yeah, it's going to be much harder to remove an electron because it's already perfect, right? We know our noble gases are perfect. So how does this affect the ionization energies across the periodic table? Oh my gosh, you guys, it looks like ionization energy, it increases as I go across a period left to right. Yes. It also increases as I go up within a group, or you could say it decreases as you drop down a group. So that means over here where my helium corner is of the periodic table is my elements who have very high ionization energies. It is going to take a lot of energy to steal an electron away from them. Lots. They want to hold on to their electrons. Versus these guys over here, they're all just loosey-goosey. They're like, whatever, take an electron from me. That sounds good. Okay. Well, let's kind of talk about what it is that's causing these trends. Let's focus in on why does this trend of ionization energy show what it shows when I'm looking within a group. So down a group, ionization energy decreases as you go down because the atom occupies more energy levels. Therefore, those outer electrons are pushed away from the nucleus from electron shielding. You guys, they're far from the nucleus. It's going to make it kind of easy to remove it because that nucleus is so far away. He's like, I cannot pull on you. You may fly away. Okay, so that means I have really low ionization energies as I drop down here. But one thing I want you guys to notice, my reason why going down a group, the more energy levels due to electron shielding, kind of the same why for my atomic radiuses trend. I'm hoping this gives me a little bit more confidence in being like, oh, maybe this won't be so terrible to remember all these whys. So let's talk about across a period. So going from left to right across a period, we know that we are adding protons. Ooh, so let's see. Ionization energy increases as you go from left to right because of an increasing nuclear charge. Wow. So we knew this made the atom be smaller, but guys, it's also increasing the ionization energy. It says, therefore, the electrons are pulled in closer. And y'all, if those electrons are pulled in closer by that tight nucleus, it's going to be very, very, very hard to remove them. Yeah. Another way I can kind of think about this, in the lesson that we learned yesterday, we always said that, oh, metals, they lose their electrons, right? And then the non-metals, they gain. This is kind of more scientifically why to explain that. I know we were using terms like, oh, we want to get to 8, but the atom doesn't want to do anything. He does not have a brain, right? All he is doing, he's not even a he, all it is doing is responding to these different changes in the electrostatic forces within the atom, okay? So this guy over here, my lithium guy, he's the one who is farthest to the left of my period, right? He's only got 3 protons. It's hard for him to hold on to the outer electron energy level. So poof, it's going to be kind of easy to remove him. Low energy is required to take off that electron. But as I cruise through 4 protons, 5 protons, 6, 7, 8, 9, 10, neon is like, I got a real strong nuclear charge. You guys in my outermost energy level, y'all come in tight. So yeah, it's going to take a lot of energy to remove those guys at the very end of my period because that nuclear charge is so strong. Okay. Ooh, that's fun. I love this stuff so much. Okay, before we do this cool thing, let's bounce down to our notes page. And I thought we could maybe draw some trend lines on our cute little mini periodic table here. I love that. Okay, here we go. Woo. Okay, so here is our trend lines, right? And our trend lines for ionic or ionization energy, as we said, that as I move from left to right, it increases because of that increasing nuclear charge. And as I move down a group, it decreases because I'm adding more energy levels, which makes the atom bigger and fatter. And woo, you can take my electrons any day. Thank you. So I'm going to draw my arrows in the direction of where ionization energy increases. Okay. So everybody up here in this top right corner has high ionization energy. Everybody down here in the bottom corner, bottom left corner, has low. Now here are my visuals over here. We like my visuals. This is showing the trend going down a group so we can visually see those energy levels being added. Well, as a result of adding energy levels, it gets easier to remove those electrons because they're further away from the nucleus. So my trend line shows ionization energy as being high at the tops of the groups and low down here at the bottom. Okay, now my across the period trend, we know that ionization energy increases, takes more energy to remove electrons from these guys because of that increasing nuclear charge. Woo. So in this direction, I have high ionization energy, right? And I have low ionization energy. Okay, this is getting fun. Now let's do our little game, which I love so much. Okay, so I'm gonna keep my little mini ionization energy trend to help me out here. Okay, so it's which has higher ionization energy, magnesium or phosphorus? Ooh, well, we know that they are in the same period is what I'm looking at here. We know ionization energy increases because that nucleus is getting stronger, which makes the atom smaller, which makes them hold on to the electrons tighter, which makes the electrons harder to remove, therefore higher ionization energy. So the answer for that is my phosphorus. Yes. All right, now I'm looking at 2 elements that are in the same group. I'm remembering my trend. As I go down, I get bigger, I get fatter. Those electrons are farther away from the nucleus, so they're going to be easier to remove. So the question is, which has the higher ionization energy? Which atom would require more energy to take an electron off of it? It's going to be the one who has fewest energy levels, the one whose energy levels are closer to the nucleus, so astatine. Cool, this is so fun. Okay. Oh, that's arsenic. Sorry, you guys. I know my elements, I promise. Okay, another learning check. It says, would it be easier to remove an electron from boron or from aluminum? So on my real periodic table, so we can actually visually see these things, we got boron, we got aluminum. We have boron, he is up higher, he is smaller, he is tighter. So it will be easier to remove an electron from the bigger, fatter element out of those two. So aluminum would be much easier. Next question is, would it be easier to remove an electron from boron or from carbon? So now we're comparing boron to carbon. So these guys are in the same period. I know things get smaller and smaller and smaller and tighter and tighter and tighter. So as I move that direction, it's going to get harder to remove, higher ionization energy. So it's going to be easier to remove the elements towards the left side of a period. So that would be boron. Next question is, which element would have a larger first ionization energy? An alkali metal, okay, so alkali metal, group 1, in period 2, so that's lithium, or an alkali metal, so same group, in period 4. So I'm comparing lithium and potassium. Who's got a larger ionization energy? Who is going to require more energy to take an electron? The smaller, tighter guy, right? So the smaller, tighter guy, my lithium guy, it's going to be the guy in period 2. All right, last question is low ionization energies are most characteristic of atoms that are... Well, we know low ionization energies is towards this corner of the periodic table. We know I have a staircase here. The staircase is the dividing line between metals and non-metals. So let's see where we're going with that. Yes, metals. So guys, this is why metals tend to form positive ions. It's not about what group you are on the periodic table. Well, I mean, it is. The periodic table was organized based on this concept, but I'm not just being like, yep, anybody in group 1. I'm not just thinking about that mindlessly. It's because these metals have low ionization energies, which means they are more likely to lose. Okay, this is getting fun. I'm really excited. Ooh, okay, we are on our last periodic trend. This is electronegativity. And electronegativity actually kind of goes hand in hand with ionization energy. This little cute little cartoon has this sodium atom. He's like, I think he's holding up one of his electrons. He's like, hey man, I am happy to share. And then chlorine is like, nope, I'm gonna steal it more. So I like to think of electronegativity as how greedy you are to grab and steal electrons. Let's see what the super sciencey definition is though. So electronegativity is a measure of the ability of an atom in a chemical compound to attract an electron. Basically, how badly does an atom want to gain another electron? Okay, when I'm talking about pulling on electrons, that's the nucleus. That's that positive nucleus, that nuclear charge that is pulling on those negative electrons. So we're wanting to see how strongly that nucleus has the ability to attract electrons. That's what electronegativity is. Let's look at the trend, or the non-science introduction and how this applies to the octet rule. Okay, let's pretend an atom with one valence electron, alkali metal. It doesn't really want to get more electrons because, man, you guys, it is so far away from 8, right? If I had to get to 8 by gaining electrons, I'm going to have 7 more electrons is required for me to do that. So if you're saying what it wants to do, bye, right? So if an atom has, say, 7 valence electrons, meaning my halogen's over here, y'all, he's so close to 8. He wants another one very badly, right? So like I said, these atoms do not have brains. They do not want or need anything. This is all about their responding to their nuclear pull, okay? So let's see how electronegativity trends across the periodic table. Now, at first glance, this is looking very similar to my ionization energy trends. I see the high stuff over here, right? I see the low stuff over here. Well, it makes sense that if it is harder to remove an electron, that atom is probably holding things on tight, that he would maybe also want to pull in other electrons. Yeah, high ionization energy tends to mean high electronegativity, but I put a big old fat X over those noble gases. So based on the definition of electronegativity, the atom's ability to want to attract an electron. Y'all, the noble gases, they have a full shell. They no thank you. We do not want any more electrons. That would require us to add another energy level, and no, we are already stable, okay? So you do see this trend as we get closer and closer and closer to getting a full valence shell, those atoms kind of become greedier, right? Well, they don't become greedier. They have no personalities or brains. So let's talk about why. Oh, my why for down a group. Electronegativity decreases as you go down a group because the atom, same thing I'm saying over and over again, occupies more energy levels. Therefore, the outer electrons are pushed away from the nucleus due to electron shielding from those inner electrons, which, y'all, is going to make it harder to attract more electrons. If my nucleus is so far away from that valence shell where any incoming electrons are going to fill into, that nuclear pull he's trying his best, but he's not going to be very effective if my energy levels are really far away. So that's why electronegativity decreases as I go down that group. That nuclear charge is just like, bye guys, I do not care anymore about you guys. Y'all are far away. Versus these guys up here, y'all. That nucleus is super close. He is pulling those electrons in tight, which means high ionization energy, right? He didn't want to lose those, but he's also able to want to attract other electrons from outside of the atom. I love this so far. Okay, let's learn about why going across the period. Electronegativity increases as you go from left to right because of an increasing nuclear charge. More protons. This is the greediness I'm talking about. When I talk about greedy atoms, I'm talking about strong nuclear charge. We know as I go from left to right, I'm increasing a proton every single time, and that means the nucleus is getting stronger, which therefore the electrons are pulled in closer, making it easier to attract more electrons. Yeah. Oh my gosh, I'm loving this so much. Let's bounce on down, let's see, to our document camera and make sure we can summarize this on our electronegativity. I'm going to use green for my electronegativity. So my electronegativity trend is the same as ionization energy, where I have my high electronegativities up here, right? And my low down here. Yes? And then we are going to put a big ol' X for my noble gases, right? So we're going to say noble gases En, that's the term or the symbol for electronegativity, equals 0. They're good. They don't want nothing. No thank you. So if I were to ask, well, I think I have a question coming up here. Maybe, yeah, I have a question coming up here that's going to ask the same thing that I was almost about to ask. So anyway, let's go over here to our summarizing our group 10. We are adding energy levels. As I add energy levels, that nucleus is like, those electrons so far away. No, thank you. I do not care. He does not need to attract. That's why I have low electronegativity down here. But as the atom gets smaller, that nucleus is going to be able to pull on those outer electrons much, much easier. So I have a high ionization energy up here. Cool. Now across my period trend, we know that electronegativity and ionization energy increase as I go across a period. So I go from low electronegativity, low wanting to get electrons to super high, except, y'all, do you see this last guy? He is a noble gas. He is neon. So we're going to put a big X on him. So it increases until you get to the noble gases. And once you get to the noble gases, it's like, no, thank you. We are not electronegative at all. Okay, so let's figure out what fun questions I'm going to ask of you. It says, which element on the periodic table is the most electronegative? Well, we know the trend increases up here to this top corner, which normally we would be like, oh yeah, that's helium. No. So electronegativity ignores all of those noble gases. So my most electronegative atom on the periodic table is actually going to be fluorine. He's the greediest for the electrons, right? Very small, very strong nuclear charge. If this question was which element on the periodic table has the highest ionization energy, remember that trend is the same. And that trend also includes the noble gases. So highest ionization energy would be helium. It would require the most energy to remove helium's electrons. But highest electronegativity is going to be fluorine, because we ignore those noble gases. So which element is the least electronegative? Well, least is the opposite corner. And y'all are like, I'm so confused with this intertransition metal. No, intertransition metals, remember, they fit in nicely right here. So actually the element that is in the bottom left corner of my periodic table is this guy right here. So we have francium is our least electronegative atom. He's also our biggest atom. He is all loosey-goosey, just big and fat over there being like, whatever, electrons, you can go. I do not care. I do not want any more of you guys. Okay. And then the last one says, why do the noble gases have an electronegativity of 0? They already have a full shell of 8 valence electrons. Okay, now if you would like, I know we got a lot of stuff going on the periodic table that we colored together this unit so far, but if you would like, you can totally add these trend lines to your periodic table, just because, as a recap or whatever, right? So my atomic and ionic radius, they show the same trend. So we would just go, yeah, and I'm actually going to use my same colors that I used to draw in my notes. But this shows the increasing of a trend. So I can literally write down here, I can write atomic and ionic radius. down here. So those are where my big, big, big atoms are. And then my electronegativity and my ionization energy increase up in this direction. So my blue was the one that I used for ionization energy. So we'll map him out first. All right. So we're going to say ion energy. I'm abbreviating like crazy there. That is okay. You guys get it. And then I used green for my electronegativity. I'm like, okay, cool. Look at us go. Right? So En. Right? And then if you want, I know your noble gases may be colored. You can just put a little note right here that they have an electronegativity equal to 0. So these are our trends. And the cool thing about these trends is the Y's are the same for all of them. All of these trends, Y's for going across a period, is due to an increasing nuclear charge. As a result of an increasing nuclear charge, the atom gets smaller. So atomic radius decreases. The atom holds on to their electrons tighter, which means it's going to take some energy to remove electrons. So ionization energy increases. And as the atom gets smaller, it becomes more greedy for electrons, right? Which means its electronegativity increases. All of those things across the period are due to increasing nuclear charge. Going down a group, all of these trends are due to adding energy levels. Adding energy levels makes the atom bigger. So that's your increasing atomic and ionic radius. And adding energy levels also makes it real easy to remove them. So decreased ionization energy, and it makes you not one anymore because it's so far from the nucleus. So decreased electronegativity. So all of these are adding energy levels. All of these are increasing nuclear charge. So that is wonderful that all of them just happen to be the same thing. Thank goodness she's not asking me to remember too many things here. Yes. So this is a really cute video. Not really cute. It's a little bit long, which is why we're not going to watch it together today. That review these periodic trends that we talked about today's lesson. Now I want to talk about how this, affects reactivity, right? So reactivity. I want to talk about reactivity, particularly of metals versus nonmetals. Now, we know that metals tend to lose electrons. That's why they become positive. How does this make sense based on the trends that we talked about today? First, I thought we would maybe like to watch a video or so on the reactivity of specifically the alkali metals.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
So that was quite a dramatic representation of reactivity, right? And I have kids every single year being like, wow, that was amazing. I can totally see lithium, sodium, potassium, rubidium, and cesium. It got so much more reactive. And y'all are like, what about francium? And I have this amazing video of this like super nerd scientist guy that I've got to show you guys because every year it makes me so happy. So we're going to watch that now.
Alkali metal tie.
You have an alkali metal tie.
It's a new tie I've just got. This one's a Dutch one. I was given it on Saturday. He gave me this one. So here you can see we have the alkali metals.
Oh, hang on, where are they? Yep.
Here. And the alkali metals are very reactive. So we've seen that lithium doesn't react very much. But then as you go to sodium, and then to potassium and rubidium, the violence of the reaction gets more and more and more. And cesium is even greater. I don't know whether the people making this tie were so frightened that they didn't put it on, but in each of these cases the reaction is removing one electron after another, one electron from the outer atom, outer shell of the atom, and the bigger the atom, the easier it is to remove the electron. And as you go down the periodic table, the size of the atom increases, so it's easier to remove the electron. So francium would almost certainly be even bigger than cesium because it's a whole row lower down, and so that should react with water with enormous violence. But unfortunately, francium is very radioactive, and you can't get a nice lump of francium the sort of size that you'd like to throw in water to make the YouTube video of the century. Francium, which is named after France, was discovered by one of Madame Curie's pupils in 1939, 5 years after Madame Curie herself died. I always thought that it was Madame Curie that discovered it, but in fact it was discovered after her death. But its properties would probably be similar to those of cesium if it was not very radioactive. But radioactivity like that makes it very difficult for chemists to study the chemistry in enormous detail. Chemical reactions are really quite sensitive to temperature, and radioactive materials, as they decay, give out energy, so the compounds themselves tend to heat up. A lump of plutonium, which is very radioactive, is really quite warm to touch. And francium, which I think is more radioactive, is probably very warm. So I think the melting point of francium will be lower than that of cesium because the melting points go down the group. And because it will be generating heat, almost certainly francium would be a liquid at room temperature. But I've never seen it. It might well be coloured as well because cesium is golden coloured, so I would not be surprised if francium was red, but I have no idea, and I'm not sure if anybody knows.
Oh man, that guy is my favorite person in the entire world. I love listening to him talk about that because did you guys hear how he said that melting point actually decreases as you go down the group? When I say melting point decreases, that means as you go down to the bigger and bigger and bigger elements, it is easier for them to melt because their melting points, or the temperature at which they would melt going from a solid to a liquid, is going to be a low temperature. That probably has to do to the loosey-goosiness of that atom already, right? I also loved how he said we don't really know what francium looks like because it is so radioactive, but he was able to predict other things. It's kind of just like what Mendeleev was doing when he first organized his little holes in his first periodic table, which is so cool. So reactivity of metals, and a summary, it says in general, the further down a group, the more reactive to metal. Reactive the metal. That's because it is easier to lose electrons. So remember the video, as you go down those alkali metals, the bigger the explosion. And that is because metals lose their electrons. Easier to do that when I get bigger and fatter. Now let's think about nonmetals. So I have a nonmetal video and see how the halogens react.
Here are the 4 halogen elements: fluorine, chlorine, bromine, and iodine. Fluorine on the left is almost colourless. Next comes chlorine, which is greenish yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid and iodine is a solid. Even so, they're both quite volatile. You can see the coloured vapours, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid or gas, the halogen elements consist of diatomic molecules, F2, Cl2, Br2 and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced: HF, HCl, HBr and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases. They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of the pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance. The products of all 4 of these reactions are white solids, and they're all trihalides: AlF3, AlCl3, AlBr3, and AlI3. Now aluminium is a trivalent element, so in these compounds the halogens are all showing a valency of 1. That valency of 1 is also satisfied when the halogen atoms bind to one another in the diatomic molecules with which I started this sequence.
Ooh, so we saw something different here with these halogens. Instead of them becoming more reactive as I went down, they became less and less and less reactive, right? Everything that he did with fluorine was like really aggressive, really fast, right? And everything that he did with iodine was probably the least intense type of reaction. Well, guys, this has everything to do with all of the trends we talked about today. And the reason why they're opposite from the metals has everything to do with the fact that nonmetals, especially these halogens, like to gain 1 electron. It is so much easier for them to do that when they are smaller, like this fluorine guy. Like he's going to be sucking in those electrons as quickly as he can, which means he's going to be very reactive. I also noticed that in the video, they said fluorine and chlorine are gases at room temperature. Bromine happens to be a liquid, and iodine is a solid. So here we're looking at how the reactivity and how the size of these atoms of the nonmetals can change what state of matter it most typically is found in at room temperature. So to recap this, it says in general, the further you go down a group, the less reactive the nonmetal. And this is because as I go down the group, it is harder to gain electrons. So it's opposite. Metals, they lose electrons. It's easier to do that when you go down a group. My nonmetals, metals lose electrons. So it's harder to do as you go down a group. And my nonmetals, they gain electrons. So that's harder. Oh my gosh, you guys. Y'all get what I'm saying. So my metals, they lose. It's easier to do that when you go down a group. My nonmetals who gain, it's easier to do that up at the top of the group. So they show the opposite trend in terms of reactivity. So the reactivity of metals and nonmetals can be explained by, remember my Y for all of my periodic trends going down a group? Those adding energy levels, which is really exciting. So I hope you really enjoyed the lesson on our periodic trends today. It is all about that increasing nuclear charge of the protons pulling everything in tight as I go across a period. And it is all about these adding more energy levels, making the atom get bigger and fatter as I go down a group. This explains everything in terms of how the elements react with things, what states of matter they are, what tendencies they do in terms of reacting with specific other elements. So welcome to the amazingness of the periodic table, and I cannot wait to see how all of this influences bonding, which is what's coming up next unit.